Hi, I'm Dr. Prathana Ghosh, and today I'm going to talk about a virtual work method to compute slope and deflection at any point in a beam or a frame. So what is our lesson objective today? Determine the slope theta at any point in a beam or frame. Determine the vertical deflection at any point in a beam, which is basically delta. And we'll also know the sign convention of slope and vertical deflection. So virtual work method is another methodology to compute slope and deflection in a beam or frame. There are several methodologies out there. So we'll discuss first the theory, how it is developed, and then we'll go through an example problem to find out slope and deflection. So let's discuss the theory first. So step-by-step analysis procedure with an example. So as the name suggests, virtual work. So what does it mean by virtual work? So we have to think about that we have given a real beam. Let's say this is the example we are seeing here. We have one cantilever beam, one side fixed, the other side is free. And we have distributed triangular loading is there in the beam. So our aim will be to find out slope and deflection at the free end of the beam, which is at A. So we need to find out delta A, the vertical deflection, and theta A. So, and length of the beam is L. So being said that, we have to create the virtual beam for that real beam. So virtual beam is a fictitious beam, as you can imagine. So question comes, how do we create virtual beam for this real beam? So to create the virtual beam, what we need to do? We have to remove all loading from your real beam, whatever the loading was there. As you see in the real beam, we had triangular distributed loading. So we'll remove the loading. Support remains same, no change in support. Length remains same. Only thing we need to apply is the unit virtual load at the point of interest. So what is the point of interest? Point A, because we are going to find out slope and vertical deflection at that point. So we have to create two virtual beams. One virtual beam to find out the deflection, another virtual beam to find out the slope at that particular point. So you cannot merge two virtual beams together to find out slope and deflection. So for finding the vertical deflection, we need to apply unit load at the point of interest, which is point A. It could be 1 kip or 1 pound in FPS system, or it could be 1 Newton or 1 kilonewton in metric system. Now, next question comes, which direction should we apply the unit load? Should we apply in the downward direction or upward direction? It is based on the deflection diagram of the real beam. So as you see, the deflection is going to be downward at point A. It is 0 at the fixed end, then it starts to deflect due to the application of the load, and it becomes maximum at the free end, which is going downward. So as the deflection is going downward, we'll apply the load in the downward direction, unit load in the downward direction. So it follows the deflection direction. Similarly, we'll create another virtual beam 2, to find the slope at that same point. If we need to find out, could have been told a different point, or you need to find out at the same point the deflection and slope. So to find out the slope, what you will do, will apply basically your moment, unit moment at that particular point. So question comes, which direction should we apply? Again, you could apply clockwise direction or counterclockwise direction. As the deflection is here going on from the tangent, as you see the slope, theta is going in the counterclockwise direction. So you could apply in the counterclockwise direction your moment. Otherwise, you could apply in the clockwise direction. And if you get negative value, obviously you'll swap the sign. So basically, it's up to you which direction you need to apply if you are confused initially. But at the end game, you need to make sure it follows the deflection diagram, basically slope deflection diagram, as well as basically vertical deflection diagram. So now is our time to go through the step-by-step analysis procedure for virtual work method. So what we need to do, we have our real beam, we need to cut at a distance x to find out our internal moment m, which we call as uppercase M, which is the real beam internal moment. Similarly, we'll find out our virtual moment in both virtual beams, virtual beam 1 and virtual beam 2, due to the application of unit load and due to application of unit virtual moment. Same distance x from the same way, the way we cut in the real beam. Again, just keep in mind, we need to follow the same way of direction. If we start from the left side and if you're cutting from the right side, and same way we'll cut in the virtual beam. We'll start from the left and we'll cut at a distance x, we'll get our virtual moment. So these virtual moments are designated as lowercase m and lowercase m sub theta. For slope, it is m sub theta. For vertical deflection, it is lowercase m. So both of them are virtual moment, internal moment, one due to application of unit load, the other one due to application of unit virtual moment. Now is our time to apply the theory of virtual work. So for finding deflection, we'll go through the theory. 1 times delta mm over ei dx, the integration over 0 to L, the whole span of the beam. And for finding slope, 1 times theta m sub theta over ei dx within the integration 0 to L, the whole span of the beam. So basically, we are multiplying the real moment with virtual moment in each of the case, and we integrate it and we get our vertical deflection and slope. EI is the flexural rigidity of the beam or frame, E is the modulus of elasticity, and I is the moment of inertia. So that gives you the idea of the virtual work theory. Now, question comes the sign convention. We already talked about that you start with your sign convention. If you get positive value, you will keep as it is. If you get negative value, then you swap the sign. So let's say you start with downward unit virtual load. Somehow you get negative value. So that means deflection is going upward. You need to swap it. Similarly, let's say you start with counterclockwise unit moment and you got negative value. So that means your slope is going clockwise. So that's basically the sign convention of virtual work. So let's go through the example problem, and then you will have your practice quiz problem that I'm showing here. After the example problem, you will have your homework practice quiz problem. This is the determine the displacement and slope at point C using the virtual work for 2 span. EI is not constant, as you see here. We have 3i for the first span, the other span is I. So just to keep in mind, when you have 2 span, you have to use 2 integration. Basically, you have to have 2 cuts within AB and within BC. So in the example, we'll do 1 cut, but in your practice quiz problem, you will have 2 cuts. So one will be x will be varying 0 to 30 feet. The other x will vary from 0 to 10 feet. Please keep in mind, it is not like shear force bending moment diagram that you have x starts from one end. You can have different x, basically different origins within AB and within BC. So x ranges within AB 0 to 30 feet. X within BC will range from 0 to 10 feet. So whatever the way you would cut within AB, same way you need to do for your virtual and real. Same thing follows BC. Whatever the side you want to cut in real beam, it will follow in the virtual beam. So let's go through the example for one section, and then you'll have your practice quiz. So I'm sharing it, and then I'm going to open the Microsoft OneNote to solve the problem. So let's do the 1 span example problem for the virtual work. So we are having a cantilever beam, as we talked about. Height of the loading is W. Downward triangular distributed load. Length is L. This is your real beam. And you have been told to find out the slope and vertical deflection at A side of the beam, which is the free end, theta A, and vertical deflection is delta A. So this is your real beam. Now we'll create the virtual beam for this real beam. So how many virtual beams? You have been told to find out delta A is how much and theta A is how much. A is constant. So let's create the virtual beam. We have two virtual beam, one virtual beam for finding that vertical deflection. So what we need to do, we'll remove the all loadings from the real beam. Length remains same, support remains same, and we'll apply the unit virtual load at the point of interest, which is point A. No other loading will be there. Similarly, you will have another virtual beam. To find out the slope, what do you apply? We'll apply basically unit virtual moment. Length is L. So we'll cut at a distance x. We'll get our moment, virtual moment. One of them will be just small m. The other one, same at a distance x, same way of cutting, the way of direction. M sub theta. And same thing we need to follow in the real beam. We'll cut at a distance x to find out our real moment. So let's find out each of the moment. So this is your virtual beam 1. This is virtual beam 2. One for your deflection. The other one for slope. So let's find out each of the moment. So first we need the virtual beam 1. Summation of m is going to be 0. M counterclockwise and 1 times x is counterclockwise. M is minus x. Similarly, the other one, we are cutting at a distance x, m sub theta is going to be 0, the moment. So m sub theta, and then counterclockwise moment 1 is going to be 0, so m sub theta is minus 1. Let's name these equations 2 and 3. So where is 1? Where 1 will be the real moment. Now we'll work on the real moment. So let's work on the real moment. So we'll cut at a distance x, remember? Same way. So what will be your new height? By similar triangular proportion, W over L times x. And your new equivalent concentrated load will be area of the triangle half. Height is W over L times x and base is x. And distance from the cut section is x over 3. And you are trying to find out your internal moment, uppercase M. So let's find out. M counterclockwise positive, and this one will create counterclockwise moment. So half W over L times x is your load and distance is x over 3. So M becomes negative Wx cube over 6L. That is equation 1, the internal real moment. So once you have all the moments, now our step will be to apply the virtual work theory. So let's do that. To find out the vertical deflection, 1 times delta A is equal to 1 over EI. EI is the flexural rigidity. 0 to L, we are integrating under the whole span of the beam, mm. One of the virtual moment and the real moment. So delta A, 1 over EI, 0 to L, negative WXQ over 6L, and small m is negative x times dx. So once you do the integration and you apply the limit, you will obtain WL4 over 30 EI. You got positive value and you apply downward loading. So basically your deflection is downward. We do not need to change any sign. Similarly, you will get our slope 1 times theta A, 1 over EI, 0 to L, m sub theta dx. M sub theta is the virtual moment in virtual beam 2, and m is the uppercase m is the real internal moment. So plug it back again, 0 to L, negative wx cube over 6L, and m sub theta is just -1 dx. So if you do the integration and put the limit, you will get WL cube over 24 EI. And again, positive value. So we started with counterclockwise moment, we got positive value, so your slope is counterclockwise. So I hope you have enjoyed the video, and I'm going to show one more time your practice quiz problem to make sure that we are on the same page. As I mentioned, you will have now 2 segments. So how many cuts you will need? 2 cuts, one within AB, so X1, that will range from 0 to 30 feet, the other one within BC, 0 to 10 feet. And so you have to perform 2 integration. One integration will be 0 to 30 feet, the other one 0 to 10 feet, and then you will add it. Another one thing you need to make sure, here EI is not constant. So whatever the EI, you need to divide by that EI in that particular segment. So for the first segment, when you divide by 3 EI, for the second segment, you are going to divide by just EI. So I hope you enjoyed the video and you can apply virtual work theory easily.